Today we continue working on linear transformations. We started on this topic yesterday, so our basic notes are on yesterday's Canvas page. Today we're going to talk in some more depth about exactly how these different transformations work. We're going to use two different colors of pencils on our notes here. I have different color ink I can use on the notes here. And we're going to go through these things in two kind of major categories. Our first category is going to be rules about vertical transformations, or you could think about vertical is our y direction. So these are transformations to y, and y is f of x. So if we transform our function f of x and we add something to it, so we take an existing function and we add to it, all we're doing is moving that function up if we're adding a positive or down if we're subtracting from it. So if we said in this format g of x equals, so a new function equals an original function f of x plus some number. What we've done is we took any number that was in that function and just slid it up, shifted it upward 3. And we talked about yesterday, our word for shifting, our formal transformation word, is translated. So we've translated that original function up 3. Or if we subtracted, we would translate it downward. And we can tell this because remember that f of x, this function thing, is basically the same as saying y. So our new y values are our old y value plus or minus whatever this new number is, this offset. So we can tell again, this is outside parentheses. So here, outside parentheses, not in parentheses. In parentheses is our input. Something happening outside parentheses is affecting our output or our y value. So that's going to translate our y values up or down when we add something to an existing function. When we make a function negative, so if g of x is the opposite of f of x, that means our new y values are all the opposite of our old y values. So let's think of how that would look. I'm going to use Desmos as the calculator today. It works very similarly to the TI calculator graphing, but it'll be a little easier for me to show and switch things around quickly. So let's say our original function was y equals x plus 2. If we make a new function that says y equals, and then we put all of that as a negative, so negative whatever the first function was, so negative x plus 2, then we're going to reflect this original pink or red graph over the x-axis. So we're going to reflect it from here down to the bottom. So basically think of all the y values. So this y was positive 2, now it's negative 2. This y was positive 1, now it's negative 1. This y was positive 7, now it's negative 7. So all of our y values, our output values, switched from positive to negative. And what that does is it causes them to reflect or mirror themselves across this horizontal axis. So if we make an entire function negative, then we're going to reflect it across the x-axis, or switch all the y's from positive to negative. The last thing we can do in terms of a function is to multiply an existing function by a number. So we could take our original function x plus 2 and multiply that by 4. What we do then is we vertically stretch that function by a factor of whatever that number is. If it's a bigger number than 1, we're stretching it out. If it's a smaller number than 1, so say it was 1 over 4, then we are compressing it down. So this is our, and remember reflect is our keyword here, and then vertical stretch and vertical compress. These are vertical changes because, again, we're talking about the y values here. We're transforming our original y values into new y values. All right, so let's do a little practice with these, and then we'll see what happens in the alternate case where we're transforming the input, not the output. But let's practice these output transformations first. So we're starting off with a function f of x equals 2x plus 3. I'm going to go ahead and graph that one over here. in Desmos and do 2x plus 3. What we want to do with that one is we're going to shift it up by 2 units. So our k value, the thing that we're adding to our function, is 2. And we're going to take our original function here, which was 2x plus 3, and we're going to take it, we're not going to change anything about what f of x was, so we're going to just keep that the same, and we're going to add 2. So we're going to add 2 to that output, whatever it was, we'll shift it up by 2, and now every point that we had moves up 2 units from the red line to the green line. Just to keep consistent with those colors, I'm going to go ahead and graph the red one as the original. And again, use straight edges here, make these better than I am, but I'm going to give just the rough idea. That was our red line, and then our green line shifts up 2 units and is parallel right next to that one. So our function notation for our new function, I'm going to say that the green function, g of x, is going to be equal to 2x plus 3, or actually in function notation, we'll say it is the original function, f of x, plus 2. So we're taking our original function and adding 2 to it. Applied function notation, we're going to actually plug in f of x and put in 2x plus 3 here and say g of x equals 2x plus 3 plus 2, and we can simplify that to say this is just g of x equals 2x plus 5. So we've shifted everything up from 3 to 5. All right, so now we're going to do a downward shift. So we're going to shift down 5 units. And over on Desmos, to switch this around, we're going to take our original function again, 2x plus 3, and we're going to take away 5. That's going to result in shifting every point down by 5 on our graph. So this red line should be the same on every one of these. It's going to go through positive 3, it's going to have this slope, and then our green line on this one is going to shift down 5, so it'll go through here and be something like that. Our function notation will be g of x equals f of x minus 5. I guess k here should be minus 5. And then our applied function notation would be g of x equals 2x plus 3 was f of x. And then from that, we're subtracting 5. So simplified, g of x equals 2x minus 2. We're just putting the 3 and the minus 5, collecting our like terms to make the minus 2. All right, we're reflecting over the x-axis now. So we have g of x equals, and let's look back at our table. To make a reflection, we make the entire f of x negative. So we need to put a negative sign in front of f of x. As an applied function notation then, we would have g of x equals negative, and then we plug in f of x, but remember the negative applies to all of f of x, so we need some parentheses, and we're going to put 2x plus 3 in the parentheses. To simplify that, we can distribute our negative sign to these two, or our negative 1 if you want to think of this as a negative 1, and we'll get g of x equals negative 2x minus 3 as our final answer. So let's go ahead to our graph. We have our original function. We're not going to have a k value or an offset here. We're going to make a negative in front of our function, and we end up flipping it over the x-axis. So you see where it met the x-axis, it's the same, but every other point, if it was above the x-axis, now it's below, and if it was below, now it's above. So we can sketch these two real quick. So we're going to go here, here, and then our reflection is going to cross the x-axis at the same point, and then it's going to be down here, so it's going to go something like that. Okay? Now we have a vertical stretch by a factor of 3. Looking back at our table to remind ourselves, when we have a vertical stretch, we're multiplying all of f of x by that factor, so a times f of x. If we're stretching by times 3, our stretch is 3, and then our function notation would be g of x equals 3 times f of x. This is 3 times all of f of x, so when we plug it in, g of x equals 3 parentheses, and then in our parentheses, just like we did before, is our original f of x, which is 2x plus 3. If we distribute this 3, it's a positive 3, we get a simplified version, g of x equals 6x plus 9. And that's going to be a vertical stretch times 3. Let's see what that looks like on our graph. So instead of a negative here, we're going to put a 3. And it looks like we have a steeper line. Remember, vertically stretching a line kind of pulls it upward and stretches it to be taller. So that looks good. So we're going to graph these two. We had an intercept of 3, and it's going up at 2. So again, something like that. Our new line has an intercept that's 3 times as high, which is way up at 9. So 3, 6, somewhere around here. And it's much steeper. So it's 3 times as steep, so it's going down to here before it reaches there. So something like that, but again, please use a straight edge, draw better lines than I can here. Okay, and then our last type of change is to vertically compress our function. We still have an a value that we multiply times the whole function, but this time, g of x is going to be a fraction of the original, so 1/4 of f of x. If we simplify, or if we do the applied version of that, we have 1/4. Again, we use the parentheses and put 2x plus 3. We'll distribute this 1/4 and come up with a simplified version, g of x equals 1/4 times 2 is 1/2 x, and then 1/4 times 3 is plus 3/4. So that would be our simplified version of that one. Let's go back to Desmos and switch this 3 to be 1/4. And what we end up with is a flatter graph. So remember, a vertical compression, we're kind of squishing it, crushing it down, and it's becoming flatter, closer to the ground or to the x-axis. So we kind of like put a weight on this red one and scrunched it down to be the green one. All right, so graphing this one, we've got our intercept, which was there. Oh, that was terrible, but you get the idea. We're just drawing what you see over here. Flatter line right there. Okay, so that's all of our types of transformations we can do to our output value. So when we're changing f of x, let's review them one more time. We had a vertical shift up, which we call a translation up, and we moved that by plus 2 if we add a value, or minus something if we subtract a value from our outputs. We had a reflection where we make our all of our y values, or our output values, negative. That negative applies to everything within the original function, and it flips it upside down so that it's mirrored over the x-axis. So we're mirroring over this axis right here. And if you look at that, can I draw a straight line here? Not exactly. So if I could draw a straight line across the x-axis, this blue line here, you would see that this is kind of a mirror line. Everything is mirrored across that line. And then the last type of change we had was stretching or compressing the function. And we do that by multiplying the entire thing, the output, by a number. If the number is bigger than 1, it stretches and gets taller. If it's smaller than 1, it compresses and gets shorter. So those are all of our y transformations, or output transformations. We called those vertical rules. We're going to call this next set horizontal rules, and they have to do with changing the x value, not changing the y value. Just like our input and output on evaluating functions, input-based things happen inside parentheses. So input happens in the parentheses. You noticed all the things last time. We had a, f of x, plus k. All of these extra things were outside of f of x, outside the parentheses. But on this one, this h right here and this b are happening inside the parentheses. So we're modifying our x values, not modifying our y values now. So we can shift or translate the function left or right. Now the really weird thing here is it's the opposite of what your brain might think. We had a vertical shift with a plus k and it went up. We had a vertical shift with a minus k and it went down. So plus is up, down is minus. That makes sense. With the x's though, it's kind of reversed because remember our function is in terms of y equals some amount of x's. So if we add to our x, it kind of does the opposite of what you would think it does. If we add h, we add a value to x here, it's going to shift left. So a plus h gives us a left translation, and a minus h gives us a right translation. So that's exactly the opposite of what you would probably think, because we think of plus x as to the right and minus x as to the left. So we have to remember this is kind of counterintuitive, and graphing it can certainly help us to remember which way things go. So checking your work on graphs here is very valuable. So we're going to translate left by adding to x and translate right by subtracting from x. Let's go ahead and look at those two examples, and then we'll come back up here instead of going through this whole table first. So our base function that we're going to use this time is f of x equals 3x minus 1. So let's make our red one 3x minus 1. And in our altered version of that, what we want to do is not affect the whole 3x minus 1 function. What we want to do is replace the x, or replace. So we're going to change x here into x plus h. So we'll put x plus, whoops, I typed that wrong, sorry. X plus, and then our shift is left 4 units, so we need to add 4. And see how even though we added 4 to the x, it moved from the red one, it moved left 4 units. It didn't move right, it moved left. So that's how we can confirm with our graph that this counterintuitive thing of x plus 4 shifting to the left kind of makes sense because we see it happen on the graph. So let's go ahead and draw what we see here. We've got a k value. This should really be an h value. So k was for vertical shifts, h is for horizontal. Let's definitely cross those out and change that to h. So our h value here is plus 4, so that's going to be a shift left 4 units. Our function notation is going to be g of x equals f of x plus h, which is x plus 4. And then to apply it, we're going to plug in x plus 4 where our input was. Remember, we're changing x now when we're doing horizontal shift or horizontal transformations. We're not changing y, we're changing x. So our new function is going to be 3. Then we plug in our transformed x. Our transformed input is x plus 4. That goes where x used to be. And then we still have this minus 1 at the end. To simplify that, we need to distribute the 3 and get 3x plus 12. So we'll get 3x plus 12 and then minus 1, so we end up with a net of plus 11. And looking at our graph, we can see the y-intercept is at 11, and it has a slope of 1, 2, 3, and 1. So yes, it has a slope of 3 and a y-intercept of 11, so that looks exactly like what we got from our graph. If we want to show that graph, we were at -1, we're going up 1, 2, 3 over 1, so something along the lines of that guy. And we are shifting to the left 1, 2, 3, 4 with the same slope, so we'll look something like that. Alright, so remember the takeaway here is plus x, x plus something, gives you a left shift, not a right shift. So now if we want to shift to the right, we need a negative h value, and we want to shift right 2, so it'll be a -2. Our function notation will be, our new function is our old function, and then it's x minus 2 instead of just x. Again, just continue hammering this home, our change is happening in the parentheses, so it's an input change. When we did a vertical change, remember the -2 would have been outside the parentheses over here, not inside the parentheses. So since it's in the parentheses, we know it's shifting the x, not the y. And our applied notation would be plug in this for x. So we have 3 times x, so 3 times, our new input is x minus 2, and then minus 1. If we distribute this 3, we get 3x minus 6, and then minus 1. Minus 6 and minus 1 gives a total of minus 7. So this is what we should see on the graph once we update it. So instead of x plus 4, our new input value, our new x, is x minus 2. And we get a shift 2 units to the right. Our final equation has a y-intercept of -7 and a slope of 3. So it looks like we simplified that correctly. It matches the graph exactly. Okay, so we have -1. We're going like that. And then we have a shift to the right 2. So we go through here like that. So that's our shift to the left and shift to the right by putting in that h value in parentheses. The next kind of change we can have is a reflection, but whereas the y, when we reversed all the y values, that was like reflecting over the x-axis. When we reverse all of the x values, so if we have an x value of 1 and then 2 and then 3, if we flip those over to the other side, 1, 2, 3, then the mirror line, the line of symmetry, is actually our y-axis. So if we have a negative inside the parentheses, when we're flipping our inputs, not flipping our outputs, we reflect over the y-axis. So same idea, except instead of flipping over x, we're flipping over y because we're reversing all of the x values. So let's go down and take a look at an example of that. We're going to reflect this one over the y-axis. So g of x equals not negative f of x, but f of negative x. Remember, this change is in the parentheses, so we're affecting our x values, not our y values. When we reflected it over the x-axis, when we changed our y's, remember that was g of x equals negative, and then we had f of x. So our negative was out of the parentheses. Now our negative is in the parentheses. All right, so our applied function notation would be g of x equals, and then we had 3, and then we're going to plug in, so our original function, remember, was 3x minus 1. So wherever x was, we're going to plug in a negative x. So 3 times negative x, and then we had a minus 1. That part remains unchanged. So 3 times negative x minus 1. If we simplify and do 3 times negative x, we get negative 3x and then minus 1. So let's take a look at what happens over here. We'll get rid of this minus 2, and we're going to put negative x. So you see that we got a reflection, but instead of the two meeting at the x-axis like they did before, now they meet at the y-axis, and this vertical axis is our mirror line. So we're reflecting everything, all of our x's, so we had positive 2x, now we have negative 2x, positive 1x, positive 1x, negative 1x, positive 2x, negative 2x. All of our x values flipped over the y-axis. So let's go ahead and draw what these are looking like. So they meet at negative 1, so both of them will cross here. We have one whose slope is going uphill, and the other whose slope is the opposite and is going downhill. So something along those lines right there. And our line of symmetry where they cross and where we're reflecting across should be this vertical axis right here. So that's our reflection for horizontal. Next thing we have is horizontal stretch and horizontal compression. Let's go back up to our rules and see how these work. We have a horizontal compression. So in terms of a line, if we treat it like a picture, remember before we had vertical stretch and vertical compression? Now we're going to talk about if we had horizontal compression and horizontal stretch. You can see that they basically do the opposite thing. A vertical stretch makes the line steeper. A horizontal compression makes the line steeper. So again, everything with x is kind of opposite of what it was for y. So a horizontal stretch makes the line flatter or less steep. So we're going to have f of b times x. So we have this b value in the parentheses. So again, we know this is changing the x because it's in parentheses, not out of parentheses. And if it's b times x and b is bigger than 1, the line still gets steeper because we have a steeper slope. But it's a horizontal compression that makes that happen. So it was kind of, again, more intuitive for y because we increased y and stretched it upward. But this time, to increase the slope and make it steeper, we're compressing the line. But if you think about a slope of 3x, whether we multiply the outside by 3 or the inside by 3, either way, it gets to be a steeper line. So let's look at examples of these. We're going to plug in b inside our parentheses, and we're going to compress it when b is bigger than 1 and stretch it when b is less than 1. So 2 examples of that one. We're going to horizontally stretch by a factor of 2. So let's get rid of this a. Remember, this is called b. A was for outside the parentheses, b is for inside. We're going to horizontally stretch by a factor of 2. And we said that, okay, that's also backwards, right? So we're going to horizontally compress by 2 if we want it to get steeper. And we're going to horizontally stretch. Wait, am I wrong? I may be wrong, sorry. Let me undo that. So we're going to horizontally stretch by a factor of 2, which is going to... So they said when b is greater than 1, we're compressing. So I feel like we have to stay consistent with our rules, we're going to go ahead and say that we're horizontally compressing by 2 because b is bigger than 1, so we're going to be having a steeper slope. And then we will say we're horizontally stretching using a factor of 1/3, and that will give us a flatter slope. So b here is going to be 2. Our function notation will be g of x equals f of, and remember b and x go together in the parentheses, so this will be 2x. And this will cause a horizontal compression because the line's going to get steeper. So g of x equals f of, and then, not f of, sorry. We're going to replace all of our x's with 2x's. So that would be 3 times 2x minus 1. So we had 3x minus 1. We're replacing the x's with 2x's. So g of x is going to be equal to 3 times 2, that's 6x, and then minus 1. So let's plug this in, see if it looks right. So we had 3x minus 1. In parentheses, we're changing this to be 2 times x. And we end up with a horizontal compression, which is like a vertical stretch. We kind of scrunched the line in left to right and made it taller. And we end up with the same y-intercept, but a steeper slope. So drawing these, we get, they both cross at -1. This one is a bit shallower, and the green one is a bit, that's terrible. That one is a bit steeper. Okay, so that's our horizontal compression, which is equivalent to or similar to an idea, a vertical stretch. So when we did a vertical stretch, we got steeper. When we do a horizontal compression, we get steeper. So now we're going to do b equals 1/3. It's going to give us g of x equals f of 1/3 x, or x over 3, but I write it as 1/3 x. G of x equals 3, and then remember we're replacing our input, our x, with 1/3 x. and then we had minus 1. So I'm just doing 3x minus 1, but replacing x with 1/3 x. Let's go over to our graph and see how that looks before we write it down. So we're going to change this 2 to a 1/3. So we end up with a horizontal stretch. We've kind of pulled it out left to right and made it wider, but that's the same or similar idea looking to a vertical compression, like when we squashed it down. So horizontal stretch looks a lot like a vertical compression. All right, so plugging this, or simplifying this, if we do 3 times 1/3 x, we get g of x equals x. So our slope should be 1 now, and then minus 1. So we have an intercept of -1 and a slope of up 1 over 1, up 1 over 1. Yeah, so that looks like we simplified that correctly. Our red line looks exactly the same as it has been, so something like that. Our green line passes through that same intercept, but goes up at a shallower slope or a flatter slope. So that is the concepts here, and the really key information is what's in these 2 tables. So if there's something that you need to kind of study and memorize, it's these horizontal rules for what happens when we put an h or a b inside the parentheses, and these vertical rules for what happens when we put a k outside parentheses, a negative, or an a outside parentheses. So whether we're modifying our y values, our outputs, or modifying our inputs or our x values. So study over those. There's some practice here for you to work on with seeing whether things are inside parentheses like here or outside parentheses like here. So this 2 times is outside parentheses, this minus 2 is outside parentheses, so those are affecting your y values, and this is affecting your x values because it's in parentheses. So try to go through and identify what transformations are occurring here, remembering that x is kind of backwards. When you think that it's going to be a positive shift, it's going left, and a negative shift goes right. And then compression and stretches are the opposite of how y works as well. So try these out, check the key on Canvas, and make sure that you're getting the concept of which things apply here.